is Walter Sensei from Montreal, and the title is idol
Sustained social mobility.
Thank you.
You're very welcome. Thank you very much. Thanks for having me. It's a pleasure to be here, as always. So this is joint work with Susumu Kato and Koei Kamaga. And we're taking what we think of as a new look at the issue of mobility. And unlike traditional approaches, where typically you look at a situation in one period compared to a situation in the following period, we look at a whole sequence of periods. Typically, roughly speaking, two types of mobility. One is with respect to a variable such as income or wealth, and another thing is so. And the other one is what we call rank mobility. If you look at a society, we divide the society in different groups, whatever workers, aristocrats, capitalists, clergy, government employees, etc. You can look at the different social standings of these groups, and you can ask yourself, how has this ranking, how mobile is this ranking? How mobile is the society in the sense that has this ranking changed over time? Now the new twist, we think it's new at least, that we try to bring into this is that we look at entire histories, and the underlying idea, the motivation is, you suppose look at a specific event, like a revolution, for example, the French Revolution in the late 18th century, or the Meiji Restoration a century later, or the dissolution of the Eastern Bloc. If you have such a singular event, how does this affect social mobility in the society, but not only in the next period, but in the future? In that sense, we ask the question not only what happens from today to tomorrow, but we ask what happens over time. If there is a change to be brought about, that is brought about by some external event, or not, I shouldn't say external, by some event, is this effect sustained, or does it fizzle out after a period? So unlike typical traditional approaches to mobility, we don't go from one period to the next, but we look at a specific given initial period, and then compare the remaining periods, the rest of history, so to speak, to this initial period. So it's not a one period to the next consideration, but an aggregate of periods, if you will, compared to the initial period. And our main result is essentially the characterization of what we call a measure of sustained social mobility. So when I say social mobility, typically what I have in mind is rank mobility, right? You rank the different groups in a society from top to bottom. Something happens that can or cannot affect this ranking, and you ask to what extent is this change that has been brought about sustained. All right, I will start out with just a more standard approach to rank mobility, and I know many of us have very different backgrounds. So if at some point something is unclear, just stop me and I'll explain. Right, so again, we'll talk about rank mobility. So what we measure is not incomes or wealth or any other attribute, it's just the ranks. So we start with a set of groups, it's called the X. So this is a set of groups in society, again, blue-collar workers, white-collar workers, clerics, the aristocracy, you name it. We assume that the number of groups is at least 3, otherwise it's too simple a problem, if you will. And we assume that these groups are ranked, right? You have people on top, again, could be aristocrats in some ways, the political class in other systems. But in general, we assume that there is a given strict total order. By a strict total order, I mean a ranking without any equal ranks. You can list them from top to bottom. And as it's an order, because they're all ranked, everything's complete, everything's comparable, everything's transitive, and there is no equal groups. So there is no equal ranks. This is a restriction, and I'll talk more about that later on. But for the time being, you will see later on why this restriction is useful, and we're certainly not the only ones employing it. So I use R for a strict total order. And this is just a subset of the Cartesian product of X with itself. The interpretation is if we have a pair X and Y in the strict total order, that means group X is ranked higher than group Y. So this means X is ranked higher than Y. Now, if you look at the just traditional rank mobility in the case of two such rankings, in our case, strict total orders, the question becomes, if you move from one ranking to another, how mobile has this society been? Has there been changes in the ranking? And if yes, how can we quantify these changes? And probably the most commonly employed measure of traditional rank mobility is the Kameny distance between relations. The Kameny distance was proposed by John Kameny in 1959 and characterized also in more details in a paper with Snell. And actually, I should mention this more recently, Burak Can and Von Storken, that was in 2018, they provided a characterization of the Kameny distance in which they use one axiom less than Kameny's original set of axioms, which is actually, I think, very interesting and a significant improvement because the axiom in question was actually not really appropriate for Kameny's own setup, because he assumed that the set of groups is fixed, is given, yet the axiom talks about what happens if you take away part of the group. Or if you take away, I should say, if you take away some of the groups and they're supposed to have equal ranks in both relations, then the axiom says, well, whatever remains should be ranked in the same way as before you took them off. But again, you can only do that if you allow the number or the set of groups to be variable. And again, John and Storken managed to get by to characterize the same distance function, the same mobility measure, without this what turns out to be a reductive property. Okay, so in principle, what we want to do is in the traditional, yeah.
Just a basic question. It's small x, each for x and y
The
is
groups.
group.
Yeah.
The group consists of people.
Yeah. The group
But the
consists.
number of people is different. What is the number of people? It's irrelevant.
That's irrelevant, yeah. And you can think about, if you look at social standing, typically the number of people in a group doesn't really matter. For example, aristocrats are usually very high up, but there are only few of them, which is what makes it so annoying that they have a high step. And so the sizes of the groups do not necessarily in general do not correlate with the step. Yeah. So what we do have for the time being is a fixed number of groups. Yeah. But we can make these comparisons for any number. Again, the only assumption we make is we only look at societies where you can distinguish at least groups. But you're right, within each group there could be, and typically will be, dramatically different numbers of people. Oh, yes. Okay, so if we want to look at mobility, if you move from one social ranking to another, again, the traditional, perhaps the most commonly used measure of rank mobility is the Kameny distance. So in general, if you want to look at a measure of mobility, rank mobility, what you want is a function E, distance, that maps the set of all pairs of these rankings into the set of non-negative numbers. It assigns a number that measures mobility. So if I use script R to denote the set of all strict total orders, then the standard traditional rank mobility measure maps R2, script R2 into R plus, And typically, this function is assumed to be a metric. That is, it satisfies the triangle inequality. It is symmetric with respect to the two objects it measures. And it is zero only if you have two identical objects. Otherwise, it's positive. So the interpretation is, if you have any two relations R and R prime, you calculate the distance between the two, and it turns out that this is greater than the distance between another pair of relations. That just means that this move from this relation to this relation entails more mobility than the move from R bar to R bar prime. Right? That's the interpretation of a distance measure in the context of traditional mobility measurement. And again, the usual suspect is what is called the Kameny distance. And the Kameny distance is defined as follows. The Kameny distance dk takes two relations, R and R prime, and it says the mobility in moving from one to the other can be calculated by looking at all the pairs that are in one and not in the other, and you look at the magnitude of this set, the cardinality of this set. The reason why this is of interest is that it has a very intuitive interpretation, because this number, the size of the difference between the two sets, between the two relations, is what you get if you calculate the number of elementary changes you have to make to move from one relation to the other. Let me explain. So, for example, if we suppose we have a society with the three groups, X, Y, and Z, right? And consider a relation R that's composed of the pairs XY, XZ, and YZ. Basically, that means X is ranked higher than Y, X is also ranked higher than Z, and Y is ranked higher than Z as well. So you have X, Y, and Z as an unambiguous strict ranking of the three groups. Now consider another ranking, R prime, where we have Y is ranked higher than Z, Y is ranked higher than X, and Z is ranked up higher than X. The distance, according to Kameny, between these two strict total orders is the size, the cardinality of the difference between these two sets. Now the difference between R and R prime is the elements that are in R and not in R prime, which is XY, XZ, and that's it, because YZ is in both of them. So the Kameny distance between those two strict total orders is 2. There's another way of getting it, because it turns out that this is precisely the number of elementary changes you have to apply in order to move from one relation to the other. Notice that that definition may seem somewhat asymmetric, because I look at the difference between R and R prime. I could do it the other way around, it wouldn't make any difference, and that is because you see these rankings to be strict. Right? If you allow for equal ranks, the story is different and it becomes more complex. Again, if we have time at the end, I'll talk about that. But for the time being, it doesn't matter whether you measure it this way or the other way around, because if you were to measure it the other way around, then you would simply get the cardinality of YZ and YX, which is also 2. So it makes no difference. Now, because our rankings are strict, I can simplify this. I can write this simply as X, Y, Z, right? There's no ambiguity. X is on top, Y is second, Z is